I'm Ramakrishna Reddy. Today we are going to discuss about an orthogonalization process due to Graham and Schmidt, two mathematicians. Together, the process is called Graham-Schmidt orthogonalization process. Graham contributed the orthogonalization process. Schmidt later normalized those vectors, so it's called a Graham-Schmidt orthogonalization process. Right. Now, suppose if you have a data, to visualize the data in a linearly independent basis, it's a tedious job. Data is more convenient and comfort to look in an orthonormal basis rather than orthogonal basis. Once it's an orthogonal basis, it's easy to convert it to an orthonormal basis. Now, Graham-Schmidt process is such a process that is, given a bunch of vectors which are linearly independent, that is, which forms a basis, then how to convert those bunch of vectors which are linearly independent into a basis which is an orthogonal basis, that is, into a bunch of same number of vectors which are orthogonal vectors. Once they are orthogonal vectors, we divide by their norm, then it becomes an orthonormal set of vectors. A set of vectors which are orthogonal, the set is called orthogonal set. We call it mathematically, in linear algebra, we call it as orthogonal basis. If they are normalized, it's called an orthonormal basis. Now let's see the process. Here is the process. Given a bunch of linearly independent vectors, now the issue is to convert them into an orthonormal set of vectors. First, we convert them into an orthogonal set of vectors. Then, converting them into an orthonormal set of vectors is a pretty simple job. The core thing lies in projection. So, you need to understand how to project a vector u onto a space spanned by another vector v bar, or how to project a vector u bar onto a space spanned by two vectors v1 bar and v2 bar, and so on and so forth. Here is the definition. The projection of a vector v bar on u bar is denoted by projection, that is projection of v bar on u bar. That's nothing but its component in the space spanned by u bar. And we have seen projection of v bar on u bar is given by v bar dot u bar by its magnitude square, mod u bar square, times u bar. This is the scaling. This is how, by this much, the vector u bar is stretched. Here is a small example. Let v bar is 1, 1 and u bar is 1, 0. Then its component, I call it a v1 bar. That is now what we are doing, we are going to project v bar on u bar. That is the span that's on the space spanned by u bar is given by v1 bar. That's what I say. It's projected vector. v1 bar equal v bar minus projection of v bar on u bar. And here is the dot product. So here is that scalar. We see that the scalar is 1. So you are going to get the 0 and 1. Okay. So the core logic is we just project those linearly independent vectors onto the space spanned by orthogonal vectors. So suppose u1, u2, u3 and so on, un are n linearly independent vectors. We want to convert them into v1, v2, v3 and so on, vn, which are orthogonal vectors. So The process is how to convert these linearly independent vectors into a bunch of set of orthogonal vectors. Start with we take somewhere we need to start now. So we take the first vector v1 bar as u1 bar itself, right? Then u2 bar equal to v2 bar minus projection of v2 bar on u1 bar, right? Here is its normalization. Similarly, so till now, two vectors, v1 and v2 are orthogonalized. Now u3 bar is nothing but we project u3 or v3 onto the space spanned by already orthogonalized vectors, right? So u3 bar equal to v3 bar minus projection of v3 bar on u1 bar and projection of v3 bar on u2 bar. Now I think you got the sequence. So u4 bar equal to v4 bar minus already projected 3 already orthogonalized 3 u1 u2 and u3 bar. We project onto the space spanned by these three vectors. So u4 bar equal to v4 bar minus projection of v4 bar on u1 bar, v4 bar on u3 bar, and v4 bar on u3 bar, right? And so on. So here is an example. Now, there are three vectors, namely v1, v2, v3, and yeah, just we are cross-checking whether they're linearly independent or not. Form a matrix whose vectors are these vectors. We'll find the determinant, and the determinant is not equal to 0 here, it's 1. So they're linearly independent. Now the issue is how to convert them into u1, u2, u3, which are orthogonal vectors. Now, the first vector, we take it as the same v1 bar itself. So u1 bar equal to v1 bar, 1 minus 1 bar. We normalize it. Now, u2 bar is, we need to project v2 on already orthogonal vector u1. That is, u2 bar equal to v2 bar minus projection of v2 bar on u1 bar. Now, here is the projection definition we have seen. So we go by definition here. It's a simple dot product. So the dot product by the magnitude square times, this is a stretching factor. So 2 by 3 is the stretching factor. So you get u2 bar plus u2 bar equal to 1 by 3, 2 by 3, and 1 by 3. Let's normalize it, then you get e2 bar. Now we need u3 bar. Simple. We need to project v3 onto the space spanned by u1 and u2. This is what u3 bar equal to v3 bar minus projection of v3 bar on u1 bar minus projection of v3 bar on u3 bar. And here is a simple dot product. You can see pretty simple. It's on the screen, and we normalize it, right? So that's the e3 bar. Now e1 bar, e2 bar, e3 bar forms an orthonormal basis, right? Now let's go through the process quickly. Here it is. v1, v2, vk are a bunch of linearly independent vectors, and we need to convert them into u1, u2, uk, same number of vectors, which are orthogonal vectors. So first what we do is we convert into an orthogonal basis, then we just normalize them, then we get an orthonormal basis. And what are the procedure we discussed earlier is kept on the slide here. You can go through, right? And here is an example. It's the same example. I put it on the slide here. Okay. So this is the final algorithm, right? So the first vector, we select the same, right? And next vector in orthogonal basis is a component of next vector in original basis orthogonal to the previously found vectors. Right? Thank you.